Hi, everyone. I'm Ming-Fei Zhao from Google Research. Today, I'm going to talk about a paper called Power of Two-Sided Recruitment in Two-Sided Markets. So this is a joint work with Yang Cai from Yale University and two of my other colleagues, Christopher Liao and Arank Mehta. So in this paper, we'll focus on two-sided markets. So two-sided markets is attributed to many important applications in real markets. So for example, stock exchange or Google DoubleClick, where the advertisers try to purchase ad slots from websites who wish to sell the slots, or also YouTube Brand Connects, a sponsored content market between brands and content creators, and also some online exchange markets such as Uber, Lyft, or Airbnb. So this is a model that we consider in the paper. So we focus on a specific two-sided market, which is called double auction. So there are multiple buyers. Each of them wants a unit of goods, and multiple sellers. Each of them owns a unit of good. So this is a Bayesian setting. So the values of all the agents are drawn from some known distribution. And the goal of this problem is to design a mechanism that achieves, that receives like values reports from the agents and facilitates trades between the agents to maximize efficiency. And in this paper, the specific efficiency metric we focus on is called gains on trade. So it is defined as the difference between the total value of the agents after trade and the total value of the agent before trade. So in this example, before trade, the total value or the total welfare is just the sum of the values of all the sellers, which is 15. And after the first two items shift to the buyer, the total value becomes 19. So the gains on trade is 4. As in other mechanism design problems, we want to ensure that the mechanism is incentive compatible, which incentivize the agent to report their values truthfully. So the very first question about two-sided market is whether we can design a mechanism that achieves the optimal gains on trade. So it turns out that in impossibility results by the seminal paper by Marston Satterthwaite proves that it is impossible to design a truthful individual rational and budget balance mechanism, even in the single buyer, single seller setting that achieves the optimal gains on trade. So in this case, the optimal gains on trade is the mechanism that trades if and only if the buyer's value exceeds the seller's cost. So in the same paper, they also developed the optimal truthful and budget balance mechanism that maximize the gains on trade, but the optimal mechanism is non-trivial and heavily depend on the agent's distributions. So given this impossibility results, there has been extensive research effort on try to design and understand a simple and approximately optimal mechanisms. So here I'm listing some of the papers in about single buyer, single seller setting. But of course, there are more papers in the general two-sided markets. So one caveat of most of these papers is that the mechanism designed in these papers are not prior-free, similar to the optimal mechanism. So then the question becomes, is if there's a nice and simple and a prior-free mechanism, then how does that mechanism performs? And there is indeed one nice prior-free mechanism. This is called like trade reduction mechanism by McAfee. So what this mechanism does is that it first sort the buyer's value in the decreasing order and the seller's value in the increasing order. And then it go over the pairs one by one by trading the largest value buyer with the lowest value seller, and so on, until it hits the point where it is the last pair where the buyer's value exceeds the seller's cost. So here, this Q is called the optimal trade size. In this case, Q is 2. And instead of trading all the first Q pairs, as in the optimal allocation, so the trade reduction mechanism trades the first Q minus one pair. So it removes the last pair, the last buyers and last seller, and um, the payment for all the traded buyer is defined as the value of the removed buyer. So in this case, so only the first buyer and seller is traded, and the buyer is paying the removed buyer's value, which is $3, and the seller is getting paid by $2, which is the value of the removed seller. So this mechanism, it's simple. It's very simple, and it's a prior-free mechanism. So, and also this mechanism is truthful and budget balanced. And since the trade reduction, like the difference between this trade reduction allocation and the optimal allocation is just the last pair, the last trade, so it can obtain gains on trade at least 1 minus 1 or Q fraction of the optimal gains on trade. So basically, if the number of if the optimal trade size is large, then it has so the trade reduction mechanism has a very good gains from trade guarantee. But in general, for general distributions in the Bayesian setting, it has no gains from trade guarantee because it might be the case that the optimal trade size is 1 with high probability. So in that case, the trade reduction has no gains from trade guarantee. So given this nice trade reduction mechanisms, so one question becomes if we can achieve more result using prior-free mechanism, right? So in this paper, we focus on this problem in a slightly different angle. So what we aim for is that if we can use recruitment. In other words, like we can augment the market with additional agents. So, and the goal is to achieve a more efficient outcome than the optimal allocation in the original setting using a prior free and simple mechanism. So, and if you're familiar with the results in one-sided auction, so this is called like a Buren-Klemper type results, right? So in single item auction, there's a seminal paper by Buren-Klemper, which proves that it is actually achievable in single item auctions. So running a second price auction which is price free, right, with one additional buyer has revenue at least the optimal revenue in the original setting. So we would like to understand if the same result is achievable in two-sided markets. So there is a nice results by Babayev, Goller, and Goncharovsky, which initialized the work of this problem. So what they show is that if the buyer distribution, so they assume that the buyers are ID and the sellers are also ID. So what they show is that if the buyer distribution is identical to the seller distribution, then in fact, you just need one extra buyer so that you can use some simple and prior-free mechanisms to beat the alt. Okay, so in the same paper, they also prove like a strong lower bound that says for general distributions, there is no finite bound. Then they study some special but very natural assumptions, which is called stochastic dominance. So here is the formal definition, but intuitively you can think of it as the buyer's distribution or the buyer's value generally is larger than the seller's value. So under this assumption, they show an upper bound on the number of buyers recruited to beat the opt. So when there is a single seller, so they prove that roughly square root of m number of buyers suffices, and for general number of sellers, the number is to the order of n times m. So the mechanism they use is called buyer tree reduction, which is a variant of the classic tree reduction. So here the only difference is that instead of always removing the last pair, what you do is that you consider the value of the next untraded buyer. So in this case, was $2. And you see if every agent accept this price. If every agent accept this price, you will use this price to trade all the Q pairs. And otherwise, you have the same, the mechanism has the same outcome as trade reduction. So one immediate thing is that this mechanism achieves at least gains on trade at least as good as the classic trade reduction, because sometimes it does not have to remove the last pair. So yeah, so coming back to the the separate bound in prior works under the stochastic dominance assumption. So the bound here is at the order of n times m, right? So the question is, can we do better? Okay. It turns out in the same paper, they also showed a lower bound even in this single seller setting. So what they show is that you need at least log m buyers to beat the opt gains from trade for any prior free mechanisms. Okay, so this kind of lower bound basically rules out any, for example, constant existence of any constant result. But one important kind of reasons why this such a lower bound exists is that in that setup, so the auction is only allowed to recruit buyers. Okay, so in other words, it can only recruit from one side of the market. Okay, so then the natural question becomes, what if we can recruit from both sides of the market? Okay, can we do better? So recruiting from like both sides of the market is actually very feasible in real applications. Think about the ride sharing applications. So the platforms can spend more money on marketing. So more riders and more drivers will be attracted to use the platform. Okay, so and in this paper we'll focus on the specific problems and understand the power of this two-sided recruitment. And it turns out what we show is that if we recruit from both sides, you just need constant number of agents, okay, constant number of buyers and sellers. Okay, so this is the main result of our paper. So we formalize this in theorem 1 here. So what it says is that if we have the stochastic dominance assumption, okay, so we can use a simple and prior free mechanism, in this case, the seller trade reduction, which is an analogous mechanisms to the buyer trade reduction. So if we use this mechanisms with constant number of additional buyers and sellers, it can achieve gains on trade, at least the optimal gains on trade in the original market. So a couple of remarks here. So as shown the lower bound in previous slides, the O1, the constant augmentation is impossible if we only augment from one side of the market. And also, people might notice that in the theorem statement, we kind of assume that the number of buyers here is at least the number of sellers. But the theorem also applies to the case where m is smaller or equal to n using buyer trade reduction. Okay, so here is just an example of illustrating the seller trade reduction where we use the value of the untraded seller as the price. Okay, so now let's come to the proof. So before coming to the proof, let me just give you present like a naive approach to illustrate the challenge of this result. So we noticed that in trade reduction, right, as we discussed in previous slide, so the trade reduction will lose at most one trade, this last pair, from the optimal allocation, right? So one of the naive approach comes as follows, like there are two steps. The first step, we will show that at least one new buyer can trade with this augmented buyer, can trade with one new seller. Okay, so there's a trade between these new agents. In the second step, we show that if the first step holds, then the optimal trade size in the augmented market will increase by 1. Okay, so in this case, since the trade reduction loses at most one trade from the optimal allocation in the augmented market, then that means it is at least as good as the opt in the original market. Okay. So it's probably not hard to see that under the stochastic assumption, the step one will hold with like very high probability, like a constant, very high constant probability. Um, but it turns out that the naive approach fails because the step two is not true. Okay, so here is an example. So in the original market, there are 3 buyers and 3 sellers. So everyone can trade with every buyer can trade with every seller. So the optimal gains from trade is 4.1. Now I'm adding a new buyer with value 2.3 and a new seller with cost 2.2. So of course they can trade with each other, but in this augmented market, the optimal trade size does not increase. So you can see it is still 3. And also if you look at this performance of seller trade reduction, so if you use the price of 2.2 to charge all the buyers, you would see that the last buyer will not accept this price. So in that case, the seller trade reduction has to remove the last pair to be able to get a truthful and budget balance mechanism. So and in this case, the seller trade reduction gets only 3.3 gains on trade, which is worse. Okay. So given the fact that this naive approach fails, so what we know is that basically there are events where the number of like the optimal trade size does not increase and the seller trade reduction has to lose a pair. So in this case, we incur some gains from trade loss, right? So we have to show there exists an event where we can use the gains on the gains on trade to cover these losses. Okay, so that's the main kind of approved kind of high level idea of the theorem. So just to make it more formal, so we will use a coupling argument where we first draw like uniform quantiles, and then we randomly assign these quantiles to the agent. And then we construct 2 structured events, one good event, one bad event, that satisfy the following conditions, right? So first, we will need, about good events, we will need this event to be a sufficient condition so that the seller trade reduction to outperforms the opt. Okay, so as we discussed in the previous slides, the event that there exists a trade among the new agents is not sufficient, right? So we have to design it carefully. And then furthermore, we show that we can lower bound the gains of the seller trade reduction compared to the opt. Okay, so and here we take the expectation over the random assignment and show that we have a lower bound on the expected gains. Okay, and also for the bad event, we will need to show that this bad event is a necessary condition for the opt to be outperform the seller trade reduction, and moreover, we are able to upper bound the loss, the expected loss. Okay. And the last condition is, of course, we need the good event to happen more often than the bad event. Okay. So why is this enough to prove the theorem? It's because since the bad event is a necessary condition, so that means in the complement of that event, so outside of that event, the seller trade reduction is always at least as good as the opt. Okay. And also, the loss inside the bad event is able to cover by the gains in the good event. Okay, so let's come to the case where let's try to explain how we construct these events. So we'll first consider the case where the number of buyers is close to a number of sellers, where we call it this M equal to theta n regime. So to define these events, we will first divide these quantiles into buckets with size 0.1 times n. Okay. And then, so we defined this I1 and I2 to be the first 2 bucket with the highest quantile, and J1 and J2 to be the last 2 quantile with the lowest, the last 2 bucket with the lowest quantile. So one important observation is, so we will, kind of define these quantiles and we will randomly assign these quantiles to the agent, right? So no matter how we assign to this agent, we will know that in the optimal allocation, all buyers in the first two buckets is going to trade with all sellers in the last two buckets. Okay, so this uses the fact that any buyer with a higher quantile can trade with a seller with lower quantile. Like basically, all the buyers in the first two bucket are able to trade with all the sellers in the last two quantile. So in that case, the optimal trade, like this red line, must be staying lower than these two buckets. Okay, so with these observations, we're able to define or construct our good event. So in this case, we define our good events as the fact that all of the following will hold. So so there are at least two new buyers in the first bucket and at least one old buyers in the second bucket. And similarly, we will need that there are at least like two new sellers in the last bucket and one new sellers in the second to last bucket. Okay, so why this thing? So why this event help us to achieve the conditions we want? So we noticed that if we have these two new buyers in the top bucket and these two new sellers in the last bucket, we can show that the optimal trade size will increase by at least two. Okay, so in this case, the seller trade reduction will have at least one more trade because it loses, at most one more, it loses at most one more trade from the optimal allocations in our command market. And this new trade will comes from this new buyers from this first bucket and the new sellers from the last bucket. So they're involved in the seller trade reduction allocation. In this case, we are able to show that, of course, we have more gains from trading seller trade reduction than the opt, and also we are able to lower bound the expected gain, which is the expected value if we for the buyer if we draw a random quantile in the first bucket, and subtracting the expected cost if we draw a uniform quantile from the last bucket. So also another good thing about this good event is that if the number of buyers close to the number of sellers, we can show that the probability of this event happens it's very big. So it's like very high constant probability. So it's probably not hard to see because as we like how we define the buckets, there are a constant number of buckets in total. So if we add enough number of, which is a constant, like a sufficiently high number of buyers, then we can expect a constant number of agents in the top bucket. So what it means is that now you can just define the event E2 as the complement event of E1. So we will achieve the fact that E1 happens more often than E2, and you're able to also expect, bound the expected loss by the same amount. So you get the proof. And one quick note here is that the classic true reduction auction mechanism also works in this case. So now let's come to the other regime where the number of buyers is much higher than the number of sellers. Okay, so now one big challenge here is that now, like if we define the same event, like the good event is this way, the probability of this event happens with very small probability, right? So this is a small one. So if you define E2 as the complement of E1, then we will not satisfy the probability condition. So we need to define a much smaller bad event, okay, to satisfy the probability of E1 is greater than probability of E2. So this is essentially a trade-off here. Like if we make the event smaller, it is easy to satisfy this probability condition, but it's harder to satisfy that it is a necessary condition for opt to be greater than seller trade reduction, and also it will becomes harder for us to satisfy that we can upper bound the loss under this event. So In this paper, we construct such an event in this as a sweet spot, so that the proof is complete. Due to time constraints, I will not go into that detail. So here is another result that we look at. Um, so basically, we're trying to understand the question of if we can go beyond ID, right? So in the first result, we require the agents to be ID, and also we have this stochastic dominance condition. So one question here is that if we can design um, if we can have any results without these assumptions. So what if we have no knowledge about the original market at all? If we can achieve any guarantees? So it turns out we can. So what we showed is that given the set of constant number of buyers and sellers, which satisfies a mild condition that each of the buyers can trade with each of the sellers with some like very small constant probability, then for any given market, if we run the true reduction on the augmented market by adding these additional buyers and sellers, then the true reduction can perform very well, like proximally optimal, very close to optimal in the augmented market. Okay, so few remark here. So we will require that the additional agents are independent, but we don't have any assumptions on the original market. Basically, the original markets can be arbitrary and can even be correlated. And also the same, so we require that the same set of additional agents applies to any market. So this is this is important because otherwise we can recruit buyers with extremely high values and sellers with extremely low values to guarantee more trades. So basically, you must design these like agents upfront before knowing the market, the original market. And of course, such a result is impossible with only one-sided recruitment or in one-sided market because the augmented agents might be completely irrelevant to the existing market, right? Let's say you add some agents, but the values of the existing markets are completely irrelevant to these values. So the augmented market is not playing a role here. So yeah, due to time limits, I will not go into the details of the proofs. So just to summarize, we study two-sided markets through two-sided recruitment. So in the ID setting, we proved that a constant number of additional agents suffices to beat the optimal gains on trade. And here are some open questions. So in this paper by Babayev, Goller, and Goncharowski, they show that in their paper they only allow to recruit from the buyer side, which is the larger side of the market. In our paper, we allow recruiting from both sides. So one interesting question is if we can achieve any results by recruiting from the smaller side of the market. And another question is if there's any lower bound for classic true reduction mechanisms. So and also we proved that we can augment to arbitrary market as long as we have those good agents that true with constant probability. So recruiting constant number of them suffices to make true reduction to be very close to optimal in the augmented market. So here is another open question: is if there is this lower bound of this result for general prior free mechanisms. Okay, that's all for my talk. Thank you for your attention.